Hi everyone, my name is Sujit and I'm a PhD student at IIT Kanpur and I'm currently being advised by Dr. Sujit Roy. My talk is about, so the title is bit oxymoron. I can understand I didn't, so I got reviews about it, but I didn't change it. I just kept it like that. Yeah. So I'll be talking about the combined approach of first testing and then different proof, mostly SMT-based proof techniques, which can help us in scaling up the system validation framework. Yeah, so you all have seen these pictures like 10,000 times and more. So this is like all like success stories of using formal techniques in system safety, like in large code bases, safety critical systems, and in hardware verifications as well, right? But there are certain applications in real world applications where these techniques can't be used directly, such as like model checking or single key execution based techniques, because it may happen that your programs may have some components that are very that are hard to model, right? Or you may not have uh, the definition of it, but you can always execute it. So for example, a program with an external call, library call, or in web API call, or maybe machine learning model. Right? And similarly, in case of hardwares, you may have components that are also difficult to model. But in all these cases, we assume that you can always execute these models, and you are provided with an input output Oracle interface, so you can query over all these models. Uh, yeah, so given with these challenges, I'll show you that key techniques that uh, I've been using in my work, and then so the first technique is, of course, you can, given a complex system, you can always create a abstract model manually and then use it in verification process. Or you can may use a simulation based like testing method for validation. Uh, the other approach I will show you later in this talk is a hybrid approach, which just combines these first two techniques. So my work sort of so, is around these three techniques. So I'm going to talk about the first one, where we'll be talking about verification of a system and chip model in the setting where we trying to prove that the given formal loaders are is safe in presence of an active adversary. And the second approach where we sort of do try to test, validate this kind of SOC using fuzzing technique only. So there is no formal techniques here. And then in the last, I'll show you that how did I combine these two ideas and to get a hybrid approach to take benefits of from the both this world for formal techniques and the test-based techniques. Okay, so this is my basically the theme of my thesis, to develop scalable solutions for this kind of complex system which has these closed box operations. Okay, so my first work where I'm trying to uh, sort of verify a format loader. Uh, so, so you may have you may have seen or known about this secure boot process in computers, or this the firmware updates in your smartphones or any um, IoT devices or uh, in the modern vehicles also. So what happens in this case is that whenever you get an software update, it has to be validated whether it is actually from the original equipment manufacturer. Right? So if not, then if it is a malicious image and your device ends up loading it, and it may compromise the whole security of the system. So this is an important uh, link in the chain of securities in different systems. Um, so, so in this work, we just took a. This is an example SOC platform. So I know that this audience is a bit in programming language and software engineering community. So I'm just dragging you towards the software, hardware testing a bit. But I'll just keep the talk as relevant as for a person from software engineering community. Okay? So, so what I'm assuming here is that the firmware loader is running in one core, and then there is an adversary that is trying to defeat uh, the loading process, and it may launch different types of attacks in parallel, and there is a boot image which you're supposed to load, and that is usually modeled as a finite state machines like this. So there are different types of attacks. So I have just mentioned two. So one can be the state hijacking attack. So you can just hijack the state and end up loading the malicious image. Or there may be a time of check and time of use attacks that can also be uh, launched by vendors. Okay, so the challenges in verification also there are a couple of challenges in case of modeling them and then specifying the properties. So there are no previous, and as far as I know, that there are no studies about how do we take care of any adversary that can launch, that can launch that is running at and uh, trying to defeat in parallel with the firmware loaders, and then of course there will be complex components in the systems that we want to model. And then in the specification side, so all the security properties are mostly hyper properties. Where, uh, like if you want to prove them, then you have to show that on multiple traces. I mean, so for example, so in hyper properties, if there is a violation, you have to show multiple traces which doesn't satisfy the property. So this class of property are not. I mean. Verifying this class of properties is a bit hard due to scalability issues. So in our approach, we sort of try to create a model where, so this is a combined model where we have transition relations from the protocol, and then this tamper function, which is all the capabilities, it models all the capabilities of an active adversary. And then we also came up with the properties which sort of could model different attacks and then try to verify it. So this is an example of time of check and time of use attack. So what I'm happening here is that so I'm just showing a valid trace, what a valid trace would look like. So it shows that any pair of traces you take where they start from the same boot image, and there is no uh, uh, attack by the adversary, and if there is a tampering by the adversary, then uh, and they both are ending with an accept state, then we should also check that the boot image has not changed the states across the execution states. So we have modeled this the protocol and all the adversary action properties in Euclid 5 modeling language. Uh, so I'm just showing part of the result. So we're able to verify that a given system uh, is free of these type of attacks. And so this is we tried on a 32-bit SOC model, and then so we're able to. So this technique was scalable because we were able to proof them in a couple of seconds. So what are the challenges is that I mean, since we tried most of the commercial tools which were automated but were not able to scale on such platforms because of properties that involve hyper properties, and also there are complex components in the system which are hard to model, hard to analyze, and and again, so we had to do manual modeling in most of the part, and then these are have some difficulties because most of the time models can be incorrect, and then modeling will also become very difficult with growing complexity of the platform. Uh, so in the next step, we just tried a complete like testing-based approach. So we just tried to see whether a fuzzing-based technique can help us with this. I mean, making the validation or testing approach more scalable. So can we find bugs uh, much faster? I mean, find bugs in a totally automated way without involving much manual effort. So the goal was so I just showed this example in the previous slide. So any counter example of this property would look like this, where uh, the image has changed at some certain point in the traces. So so all we need to do is to find a counter example, a pair of counter examples. Essentially, right? So if we find this, then we know there is a way or there is a security violation possible in the system. Yeah, so just an overview about first system. So fuzzy technique. So you start with a pool of random inputs, and then you have a mutation operation. This mutates this input, and you run the program, and you see if it crashes or not. If it crashes, then you see if the coverage is increased, then you keep it for the next round of mutation, or you discard it. So this method has been proven like quite a success in testing large software systems. And there have been work on, for example, RFuzz, which was appeared in ICCAD. So they tried to use those fuzzing techniques in testing hardware components. So we saw that this can also be used in sort of validating security properties in SOCs. So on with that idea, we tried to build a testing framework where we have one pipeline which where we do not have any interference from the adversary, and if we use fuzzer as an active adversary to generate uh, inputs for on behalf of the adversary, and then we sort of simulate all the traces, and then we try to validate these traces to check where does there exist a pair of traces which sort of violates the hyper property. So in this case, we also gave an new type of specific language which is based on hyper-radial but in the past time. Uh, so so the testing technique, I mean, is fully automated, but it's not a silver bullet for all the problems. But it has all its limitations as well. So this is not that intelligent or smart like the uh, the format techniques. So we thought, can we sort of combine these two formal approach and then test-based approach to find a solution uh, for our any validation framework. So our idea is to uh, so our idea is to combining this SMT fuzzing with inside the SMT solver. So any verification or any framework, testing framework that now can use which uses SMT solving can also now use this our tool to sort of do both combined and fuzzing. So where the systems that are hard to model or hard to analyze using formal techniques, so that we can sort of use the close box use that component as a close box function, which of course has an interface to query the input-output behaviors, and then we can use our tool just to on as a backend just to um, simplify this. I mean, so this will just make a bit easier for those frameworks to work on this complex components. So yeah, so our talk will be so this paper has published in Uppsala and this year, and I'll be giving this talk on Saturday at 2 p.m. in the auditorium. So please attend if you find it interesting. Yeah, so I just briefly told about the approach. So we're just combining these two uh, very tool-based approach and then first approach to get a hybrid approach so that we can use in different analysis frameworks. So our idea is to provide uh, a kind of a solver which is built on top of uninterpreted function theory. So and then so then it is sort of combined with the SMT engine of SMT solver, which then interacts with the other solvers. So if you give an SMT query, uh, it will just purify those SMT queries and separate out what the SMT solver needs to solve and what queries that we need to solve by the fuzzer, and then we sort of use SMT solving and fuzzing in synergy to find out an satisfiable instance for our SMT queries. Oh, sorry, I think there is an issue with the plots. Uh, sure, but yeah. So let me just tell what happening is. So our tool is named Sādhak. Uh, this uses a combined approach, and then there are tools which are assembly driven, and we also have a fuzz only technique. So this is what we found that this approach was uh, performing better for finding satisfiable solution. That remains the bugs in if there is a bug in the system, it will be able to find it much quicker than other approach. Of course, if that system involves much complex components. Yeah. So my next future directions are to use this tool in testing the whole SOC framework that I showed in earlier. Not, I mean, not fully manually or fuzz only technique, but the combined approach. If we can want to see whether this technique can scale for these type of platforms, and as well, I also want to see that if we can use this technique for hybrid technique for finding violations of case safety properties in the program that involves closed box components. So with that, I'll just stop my talk. So if you have any questions.
Yeah, I have two questions actually. So the first one goes back to this definition of an active adversary. Could you elaborate a little what that means exactly? So what I understood is that active in this case means that you can't really distinguish the adversarial behavior from the system behavior, and you somehow build a model which includes this adversarial behavior?
Yeah, so if I just tell what is it? So from my definition,
Yeah.
so if it is a side channel attack, so side channel based attack where you can just observe the system outputs and then tell leak some information. Right?
Okay.
So there, the adversary is just observing; it's not doing any actions. But here we are assuming that the adversary is performing an action when the system is executed. For example, in the example that I showed, so there is a firmware loader which is running and the adversary is trying to defeat it by performing some actions. There may be some tampering actions on the system or different components of the system, or it can send instructions to different components to act on its behalf.
Okay. Thank you. should we just ask the second question?
Yeah.
Okay. I'm afraid I also didn't completely understand the last part about combining SMT solving and fuzzing. So, how do you decide which parts are passed to the SMT solver and which parts are passed to the fuzzing engine, and why?
So yeah, so that the user has to decide. So suppose there is a component which is you can't really model it with SMT, or you can model, but then it sort of blows up the verification conditions. So you can just sort of abstract it out with the closed function, and then you define that this particular component is user the closed function. When you generate the verification condition, tool will know that this is a so it's sort of like a UF type, but we also provide the techniques to define support to define what function to be used as a closure function. Then our solver will detect that and then purify them and then so this is sort of a theory combination technique in using some solving, but purify different theory terms to be solved in different solvers. So similarly, the closure solver will have the information. And then
Okay, so let me ask you the same question I asked Sumit. So, eventually you'll write a thesis. Eventually you'll write a thesis.
Yeah.
You'll defend that. Like, what's going to be in there? Like, what do you still have to do? What's your plan for doing that?
yeah, so this work was a bit important for me because I think was not able to show the picture. I didn't know why it didn't come up in the website, but the results were a bit exciting. So I think I can use that in the first work that I showed. So where we were doing a lot of manual work to verify a system. Now since we can sort of abstract them with this closed box function, then we can have a sort of very automated technique to deal with such large complex problems. So then if I can do the first point that I showed, then I think that will be close cycle what we do.
And then you actually have a tool that you can apply to like.
So now that tool can be used as so it's a assembly-based technique. So now you can just plug it in any framework that uses assembly solving. So the tool that I use in the first was UK5. So also uses CQ in the backend. Now I can just try to use my tool instead of this tool.
Any more questions or the talk or advice of the overall stuff? Oh, okay. Thank you, Sādhak.